So until now we've seen a few ways of executing the same nodes over and over again. The for loop for executing a node tree a given amount of times on the same frame, and the subsolver to incrementally execute the same node tree on a previous frame's data. In this video, I want to present you a third way of iteratively running the same nodes over and over again over a given piece of geometry data, which is the infamous for each loop. Let me give you quite a stupid example, and I'll tell you in a second why that is stupid. Let's drop down a pig head, just a test geometry, dive in there, and set its difficulty to easy, so we only get this very plain mesh. And then let's subdivide this just one level. So we have this geometry. Now let's drop down a for each loop, in our case a for each primitive. And when we middle mouse on the subdivide node here, we're seeing this geometry consists out of 3,512 primitives. The primitives being those individual polygons here. So let's wire this into our for each. And in here, let's line this up, zoom out a bit. Let's just drop down a color node, which we're going to set to primitive and to random. Let's just drop this in here and highlight the for each end. And after a short while, you'll see this colored pig head now, with every primitive having the same color. So what this for each does is it deconstructs this geometry stream coming in here and runs 3,512 times and executes the color node for each of those individual polygons here. However, while running over all these polygons, we do not alter its seed. To do that, let's just mark the for each begin and click create meta import node, which creates this third node. We already talked about this when we middle mouse on it. We can access the iteration and num-iterations attributes as a detail attribute. So in the color here, to vary our seed with each iteration, let's just use the iteration attribute coming in through this node here as its seed, using the detail expression that we already know. First pointing to our node, in this case the for each begin metadata, comma, then the attribute's name that we want to use, in our case iteration, and then just the index of the attribute, which is 0 in our case, because it's just a single attribute and not a vector. And now that we've done this, we are seeing this colorized and brightly colored mesh. So now what we're doing is, and let me just highlight the for each end, check single pass. What we are doing is, in each iteration here for the for each loop, we are just taking a single polygon and applying this randomized color to it, with the seed being varied to our current iteration. Let's uncheck the single pass here and let this run over the whole mesh, which is this. Why is this stupid? For one, we could just use a color node here, which we'll wire up, set it to run over primitive, and set it to be random, and it'll automatically randomize the color of each primitive. However, in some instances, there might be functions which do not exhibit this behavior, and then you'd use either a wrangle, in this case a primitive wrangle, or a VOP. And I promised you to do as little back as possible, so let's use a VOP here, just dropping down a primitive VOP, and just stupidly building this randomized color in here as well. Just highlight this, dive in there. And in this case, I want to use my random node here. Just going to drop this down and set it to a 1D integer input, that is the primitive number, ranging from 0 to 3,511. And we want to output a 3D color. So let's wire the primitive number into the random's input and the output value into our primitive's color diffuse, like so. And immediately we're seeing a very similar result to this here. Slightly different as the random generator works a bit differently in here, but close enough. All right, let's drop down 3 transforms. Let's translate 1 to -3, like this, highlight it, copy it, wire in our color node here, which will translate to -1, and copy it again. The for each loop will translate that to 1. And finally, we'll merge those 3 heads, so we can see similar results. However, let's benchmark this. Go to the performance monitor, let's record this, and in this case, let's highlight our subdivide node and decrease and maybe increase our subdivision again. Now, when we head to our performance monitor, we can see, when we dial this down, that by far the slowest method here is the one with the for each loop, because splitting your geometry apart into individual primitives is expensive on the one hand, and on the other hand, this whole loop here is being executed single-threadedly. So we are waiting for each primitive to be finished before we start the other one. While the color, as well as the primitive VOP here, they run multi-threaded. So the whole geostream is split apart into individual primitives, which are treated in parallel. And depending how many cores on your CPU you have, this will be way faster than this single-threaded execution here. And yes, there are ways to multi-thread these for each loops. However, those in most cases are still slower than a primitive wrangle or a wrangle in general. So once you're diving deeper into production setups that see heavy use or which rely on being somewhat quick, that's usually the point when you want to dive into vex or at least VOPs and try to build the tree that you have in your for each loop purely using those VOPs in here or the vex scripting language. Let's build a slightly more sensible example, again using our pig head. So let's just drop down that pig head, dive in there. Again, I want to set it to be easy and then subdivide it. just one level of subdivision, so we end up here. And this time again, I'm going to use a foreach primitive loop here, which I'll wire in after the subdivide node. And in here, I'm going to drop down a transform node. Wire this in here, and on my foreach begin, I want to create a meta import node again, so I can access that iteration attribute here. And what I want to do here is use that transform node and rotate each primitive, so each polygon here, basically by its primitive number. So I'll take the metadata's iteration here and just pipe it into our rotation slots here. So again, using the detail expression, I'm going to access this attribute called iteration. Again, index of 0, which in this case it's 0, so let's highlight this. And now we can see this is happening. Let's add a controller where we can dial in the intensity of this. So let's create a null, call this one controller, and maybe color it red, so we know there's something to switch on here, or to dial in here. And with the controller highlighted, I want to head up here to this cogwheel symbol and go to Edit Parameter Interface, which brings up this window. And in here, I can basically build an interface on any of those nodes. In this case, I just want to drag over a float, give it a name of maybe rot amp for rotation amplitude, and call it rotation. Hit apply and accept. So we now created this slider here. It's not doing much now, so let's right click on it, go to copy parameter, and in our transform here, let's click on the name, so it brings up the expression here. Let's go back here and tap down a star to multiply, and then right click and paste relative reference. So now we pasted a link to this controller's value here, and we are multiplying our current rotation, which is derived from a primitive number coming in here, with our controller's value. And as this controller's value is currently 0, nothing is happening, but as soon as we dial this up, we can see our pig head disintegrating and the individual parts being rotated in space. We could just go to the edit parameter interface again and add 2 other float sliders. Call this one rotation X, hit apply. The second one, let's call this one rotation Y. And the third one, let's call it rotation Z. Take note that we do not need to change these parameter names. However, if you're building more elaborate setups, you want to change those to something that makes a bit more sense than new parameter. In our case, I'm just going to hit apply and accept, and I'm going to be lazy. And in my transform, I'm just going to highlight this whole expression, hit Control C to copy this, and paste it here and here. And in my controller, I'm just going to right click on my rotation Y, copy that parameter, go into my transform second slot here, delete this expression, right click in here and go to paste relative reference. You want to do this same procedure with the rotation Z, copy parameter, go to our transform, highlight this last thing, delete anything after the multiplication symbol, right click, paste relative reference. So now I can dial in the strength, the rotation strength along each axis, this time being the y-axis and this being the z-axis. So now what we can do is over time set a few keyframes and animate this disintegrating pig head. The reason why I'd call this setup slightly more sensible is that transformations can be a bit of a burden when you're trying to script them, usually involving either matrices or quaternions, which are sometimes not the most intuitive way to think about rotations. So sometimes you could feel tempted to do something like this. However, as you notice here, when we are dialing in those values with the sliders, it is not the fastest setup on earth. So again, you might want to rewrite this once you're going into production. If you guys like what we're doing and want to support us, you might want to head over to our Patreon, and we'd like to thank all of our patrons, especially Refik Anadol, Chris Hebert, Important Looking Pirates, Encore VFX, Patrick Fillion, and Gearbox Studio Quebec. Thanks so much, guys.